But now we can ask what are the things that have to happen for the uncertainty principle to be saturated. That is that you really have delta A, delta B equal to this quantity. So when can we saturate? We saturate it. Okay. What do we need? First, we need Schwarz inequality saturation. So F and G must be states that are proportional to each other. So we need that Schwarz is saturated. Schwarz saturates. Which means that G is some number times F, where beta is a complex number. This is complex vector spaces, so parallel means multiply by a complex number. That's still a parallel vector. So this is the saturation of Schwarz. Now, what else do we need? Well, we need that this quantity be 0 as well. That the real part of this thing is equal to 0. Otherwise, you really cannot reach it. The true inequality is this. So if you have Schwarz, you've saturated. This thing is equal to this thing. The left-hand side is equal to this whole right-hand side. Schwarz buys you that. But now we want this to be just equal to that. So this thing must be 0. So the real part of F overlap G of Fg must be 0. What does that mean? It means that Fg plus Gf must be 0. But now we know what G is, so we can plug it here. So G is beta times F. Beta goes out, and you get beta F. Now, when you form the bra G, beta becomes beta star. So you get beta star FF equals 0. And since F need not be equal to 0, have 0 norm, because there is some uncertainty, presumably, you have that beta plus beta star is equal to 0, or real of beta is equal to 0. So that's it. It's not that bad. You need two things: that the F and G vectors be parallel with a complex constant, but actually that constant must be purely imaginary. So beta is purely imaginary. That is, beta is equal to I lambda with lambda real. And we then are in shape. So for saturation, we need just G to be that, and G to be beta F. So let me write that equation. Over here. So G, what was G? Is B, oops. B minus absolute value of B on psi, which is G, must be equal to beta, which is I lambda, A minus absolute value of A on psi. condition. So this is the final condition for saturation. Saturation. Now that's a strange looking equation. It's not all that obvious how you're even supposed to begin solving it. Why is that? Well, you're trying to look for a psi, and you have a constraint on a psi. The psi must satisfy this. But in principle, what do you have to do? You have some kind of differential equation, because you have, say, x and p, and you want to saturate. So this is x, and this is p. Since p, you want to use a coordinate representation, this will be a derivative, and this will be a multiplication, so you'll get a differential equation on the wave function. So you write an ansatz for the wave function. You must calculate the expectation value of b, you must calculate the expectation value of a, and then plug into this equation and try to see if your ansatz allows a solution. And a solution with some number here, lambda. Well, at least one thing I can tell you before you try this too hard, this lambda is essentially fixed. Because we can take the norm of this equation, and that's an interesting fact. Take the norm. And what is the norm of this? This is delta B, the norm of this state. And the norm of I lambda, well, norm of I is 1. Norm of lambda is absolute value of lambda, because lambda was real. And you have delta B, here, of psi, of course. So lambda can be either plus or minus delta B of psi over delta A of psi. So that's not an arbitrary constant. It's fixed by the equation already in terms of things that you know.